Welcome to Lecture 10, Part 1 for Chemistry 418, Radiochemistry. This lecture is on radiation reactions. We're going to talk about dosimetry and hot atom chemistry. This is going to be the last lecture where we're going to focus on radiation effects and talking about the nucleus and the decay and properties of the nucleus. After this lecture for the course, we'll talk about chemical effects. The next lecture will be on speciation. Then we'll really focus on the chemistry of radioactive elements. The readings for Lecture 10 are in Modern Nuclear Chemistry, Chapter 16 and Chapter 17. Chapter 17 is on nuclear detectors. Chapter 16 is on interaction of radiation with matter. Nuclear detectors work by exploiting that interaction of radiation with matter. So both chapters together give you a very full picture of the interactions and radiation reactions. There's also discussions in Nuclear and Radiochemistry, Chapter 6 and Chapter 11C. Part 1 of the lecture on radiation reactions is going to cover the interaction of radiation with matter. It's going to talk about different reactions based upon the particle. So we'll discuss neutrons. Obviously the big difference with neutrons is no need to overcome a charge barrier. We'll talk about positive ions, alpha particles, electrons, negative ions. Then we'll also talk about photon interactions. Part 2, we will discuss dosimetry, which is quantifying those interactions and how it relates to radiation protection. And then we'll end Lecture 10 with hot atom chemistry. And hot atom chemistry is utilizing the nuclear reaction as the first step in a chemical process. So for instance, separations, where you do the nuclear reaction, where you allow the nuclear reaction to have a role in the first separations. So ending this lecture with hot atom chemistry is a good link between radiation, radioactive decay, nuclear properties, and chemistry and chemical properties. We've already learned about some interactions as far as different types of interactions based upon the particles. Alpha, beta, gamma. We know that alpha particles can be stopped with a piece of paper. They have high interactions. Beta particles, they need something like a piece of plastic, maybe something a little bit more robust than a piece of paper, but beta particles can also be stopped. Then we have gamma rays. We know that gamma rays have a very long path lengths, and they need lead or steel or heavier Z material to stop their progress. And we're going to learn about how these different particles would interact with matter. The fundamental basic thing we're going to learn in this lecture is that some sort of ionizing radiation comes in and it hits an atom, part of a molecule, and an ion pair is formed. We have a negative ion, for instance, a free electron, and then a positive ion. Well, it could be the molecule or an atom that has lost an electron. And we have this ion pair formed, and it's this interaction of the ion pair with material around it, whether it's structural material, biological material, water, that really drives the interactions between radiation and matter to a host of levels. But what we're going to do, we're going to focus on this initial ionizing radiation as the ion comes in, how it interacts, and then biological effects are extensions of how these negative ions or positive ions interact with the surrounding media, can form secondary molecules that can also have interactions with biological materials. One of the more interesting interactions of radiation is with water, particularly in terms of biological systems. It's really the ionization of water that drives biological effects that are of interest when we talk about health effects or dosimetry. In essence, for instance, consider a biological system like a person. We're fundamentally bags of water that have organic molecules in them. As we described in earlier lectures and previously in this lecture, ionizing radiation can come in and interact with a molecule. In this case, water. Negative and positive ions can form. And we can also, from those reactions, we can also form other molecules that can have biological effects. So for instance, this water can form excited water, which can then react. It can form radicals, such as a hydroxyl radical, a hydrogen radical, a superoxide radical. These may be relatively short-lived, but when they hit other molecules, they can in turn react those molecules. And some of these molecules that can then be formed could be something like peroxides. All these molecules, once water is ionized by some radiation, these molecules can interact with other molecules, including organic molecules in a biological system. So for instance, if one has cells in a system, it isn't necessary, and when it causes radiation damage to the cells, let's say you want to, the cell has induced cell death by damage to the DNA, it's not necessary that the ionizing radiation comes in and directly damages the DNA. The ionizing radiation can come in making a path of reactive water. This water forms a number of different compounds, and then it's these compounds that can go and then react with something like DNA. So it's really the radicals that are formed by the interaction of water that drive the reactions that induce these biological effects. And you can imagine each of these have different lifetimes. Radicals tend to be very short-lived. Peroxides can be longer-lived. So imagine an ionizing radiation racing through water, interacting with these water molecules. In the path, there's an initial ionization path. Then from this path spreads out molecules that can interact with biological material, and the width of this path will be dictated by the lifetime of the molecules that are formed. So when you form something that's longer lived like peroxide, the width increases. So this path length can deliver this energy which causes water ionization, and then that ionized water forms molecules which spread out and then can interact with molecular substances within the biological matrix. Interactions of radiation with matter, as we showed in the previous slide, where the interactions are some radiation, the matter itself is water, have some pretty similar commonalities. You get dissociation of molecules, and these molecules become excited, and then these excited molecules can also become ionized. For detection, this ionization is easily measured, and that's actually the route that we use for radiation detection. In air, about 35 eV of energy is formed and dissipated for each ion pair. Other gases have different values. Those are listed here. But fundamentally, the interactions ultimately have the same sort of effect. And the formation of ions is what can be used to detect radiation by radiation detectors. And basically, if you measure the total number of ions produced, since the ionization is a function of energy, I can determine the total energy from that particle that's producing the ionization. So there are three commonalities with radiation interaction, and this overview provides these commonalities. At high enough energies, the ion is bare. So for instance, if it's an alpha particle or a proton, and energy loss is through electronic excitation and ionization of stopping material. So if something is highly ionized and it goes through matter, it'll take off electrons from that matter. At velocities comparable to the K-shell electron of the stopping material, ions begin to pick up electrons. Stopping is still electronic at this point. And then at velocities comparable to the valence electrons, elastic collisions count for energy loss, and this is nuclear stopping. There's really no sharp difference between the second point and the third point. Let's review the interactions of certain particles with matter. We'll start with neutrons. Neutrons, they're neutral. There's very little interactions with electrons. The interaction is primarily confined to nuclear effects, so we can have scattering of neutrons, both elastic and inelastic. Nuclear reactions, so N gamma, NP, etc. listed here, and another nuclear reaction being fission. And as you can imagine, particularly the nuclear reactions, the N gamma or the N fission, provide signals for those interactions and can be used as a method for detecting neutrons. If we talk about positive ions, so think of an alpha particle, those processes of energy loss are primarily through interactions with electrons. You can talk about something about a maximum velocity imparted to electrons being twice the velocity. So if you consider energy from a 6 MeV alpha to an electron, the average energy from ions to electrons is on the order of 100 to 200 electron volts. This can also lead to ionization from that electron, so we can have secondary ionization. So an alpha particle come in, impart some energy to an electron, and that electron can then impart energy to other electrons. So we get secondary ionization as a result of some of these interactions. Electronic stopping, which we've talked about already, are inelastic collisions between bound electrons and the ion. We can get an excitation of the atomic electrons from this reaction. And the nuclear stopping, when the velocity of the ion is close to the valence electrons, we can get elastic collisions. So that was these cases, electronic and nuclear stopping, that we discussed on the earlier slide. And we've also discussed the influence of velocity. So when the velocity of the ion is comparable to the K shell, the ion will begin to pick up electrons. So something passing through matter will be able to pick up electrons once that particle's velocity is on the order of the K shell electron. This is going to have an influence on particles interacting with different types of matter. As we discussed, there's an influence on the particle, its velocity, and the velocity of the K shell electrons. So there's actually an influence on the particle moving through different types of matter. And one of the things that we will see is that the distance that a positive ion travels in matter is actually within a pretty narrow limit. That's what's shown here. If we look at this figure, it shows the number of particles at a given distance from the source. We see that number remains fairly constant, and then as you come to the part where the distance that can be reached in the material, that number rapidly drops off. And this is really driven by the fact that, particularly for positive particles, you have relatively large masses. So when an alpha particle collides with an electron, bulk of the mass is with the alpha particle. You don't get much in the way of straggling. So fluctuations along this path, along the x-axis, is minimalized. When straggling is large, this range, as you can imagine, can vary greatly. Another way to evaluate range is through stopping power. This is the relationship between energy of a positive ion and the range as seen in the change of energy as a function of distance. As you can see here, this figure is fundamentally the inverse of the range, where this line is fairly flat, and then towards the end of its range we see a large ionization. Very similar to what we just saw in the previous slide regarding range. And this is a maximum rate of energy loss, and we see that it occurs with low energies. That explains what we saw in the previous slide. We can evaluate energy loss per distance traveled of the charged particles through a given material. And there's relativistic and non-relativistic approaches. For us, we have some equations here which talk about the change in energy with distance as a function of these equations here. We see we have two of them, where our relativistic velocity is just our velocity divided by the speed of light, and when the velocity is when the relativistic velocity is much less than 1, it can collapse down to this equation, so it's non-relativistic. But the terms are the average fraction of electrons stripped off an ion, which is this term here, the ion charge, the number of atoms per unit volume of the absorber, in other words, what the ion's hitting, the Z of the absorber, the mass of the electron, and the ion velocity. Then we also have this effective ionization potential. This term is shown here in the equation. Fundamentally, we can utilize these equations to determine something related to the change in energy with distance in the material. And using this, we can get an idea of how far a particle of a certain energy can travel through material. As an example of this concept, we're looking at the stopping power of a range of ions, everything from hydrogen to fermium, in aluminum. And we're looking at this stopping power, change of energy with distance, and this unit is MeV per milligrams centimeter squared, and as a function of energy. Now the energy is MeV divided by AMU, and we do see some trends in this energy at extremely high energies, so we're on the order of 600s, hundreds of MeV per AMU. All the ions have very similar behavior. As the ions slow, the interactions begin to increase and the behavior starts to spread out. So as details, these rate of energy loss differs for different ions with the same energy. As an example here, for two different isotopes of oxygen, nitrogen-14 going 80 MeV in aluminum, we see that they have different stopping powers of about 3.5 to 2.5 MeV per milligram squared per centimeter. So this unit listed here. One can also use the stopping power to determine range of particles in matter. There's a program that's available on the web. It's called E-star or P-star, E for electron, P for proton, and it's from the NIST site, and it'll provide very good information on stopping power as a function of energy for protons and electrons in a large range of matter. And we'll go over here a very simple equation to get an idea of how much material is needed to slow down or stop particles. The calculations we're going to do is a reasonable estimate. It's not, there are other more detailed calculations, there's programs available that can provide more detailed information, but for first approximation, these equations that we're going to discuss are fairly robust and they have good utility. So your general equation is shown here that a particle, so for instance, let's focus on proton stopping in carbon, and we're going to use graphite as opposed to amorphous carbon. The energy loss is equal to the stopping power times the thickness, which will be T, and the density of the material. And as we see for carbon, we have the density of the graphite. So we want to determine the stopping power from the different particle energies. So in other words, we would go to this program, the P-star program. We can actually input the energy that we're interested in. In this case, let's see how much graphite is needed to stop 10 MeV proton. So if their energy loss is equal to stopping power times thickness times density, well, we want to say our energy loss, we solve for 10 MeV proton, we want to say that the energy loss is 10 MeV. So into this equation, we want to solve for T. So we set E for energy loss is 10 MeV. We get the stopping power for 10 MeV. We use this density shown here, and we solve for the thickness. If I go to this program, I can see a graph that'll give me information on stopping power versus energy. I can actually get the table out. I can I can request that the energy for 10 MeV is explicitly presented. And from there, I get the stopping power for 10 MeV protons in carbon is 4 times 10 to the first MeV centimeters squared per gram. My energy loss is 10. My density is 1.7. I plug that into the equation, and I get about 0.144 centimeters of graphite is necessary to stop this 10 MeV proton. I can do the same sort of equation with uranium. I look up the stopping power for a proton in uranium at 10 MeV. I get 1.7 times 10 to the first MeV per centimeter squared per gram. The density is much higher than I get for my carbon. So I put this into the equation, 10 MeV divided by the stopping power times the density. And I see that I need a lot less uranium to stop this to stop this proton than carbon. This is true. This was why shielding is often dense material, and that really has to do with the number of electrons that are available to interact with the particle. Now electrons, they're also charged particles, negatively charged. They have similar energy loss mechanisms to positive ions. Again, as we already talked about, the average ion pair formation is about 35 electron volts in air. Number of secondary ionization. One of the major differences, however, between an electron and the positive particles we were talking about is mass. So for the same energy, this means that electron will have a higher velocity that will relate to it having a lower stopping power. When an electron reaches about 150 electron volts, you get almost 6,000 ion pairs per milligram centimeter squared formed. So similar to that range figure we showed for an alpha particle, the electron will have the same thing, but once it reaches a certain energy, stopping increases dramatically. Electrons can also lose a large fraction of their energy in a single collision. And since their mass is less, we expect straggling to be much more pronounced than the example we were discussing with alpha particles. One example of some of the differences in behavior with electrons is given here for electron backscattering. We use this with microscopy to evaluate information related to the Z of the material that's under examination. A significant fraction of electrons may be reflected from scattering. And one of the things we actually evaluate is there's an increase in backscattering with the atomic number of a material. So imagine that you can determine a backscattering coefficient, and along this figure, you can figure out the Z of the material that's causing the backscatter. And coupling this with microscopy, backscattering is a method to determine composition of samples under examination. A broad overview of electron stopping power is shown here. This is electron stopping power in air. We discussed this on 2 slides earlier. We see that we get a maximum ionization at a relatively low energy. At higher energies, the ionizations are fairly constant. So as for an electron, as it slows down, we see that there's increase of interactions with air as a function of energy, where we get this maximum at lower energies. This is similar to what we've seen with Bragg peaks and interactions of other particles with matter. And similar that we performed with protons, we can also evaluate electron stopping in material using the E-star program, which is shown here. So E-star is for electron as opposed to P-star for proton. And similar to what we did for the proton calculation, we'll just look at an energy loss of an electron through some material. So let's get some data for 1 MeV electron as it travels through 0.1 millimeter of uranium metal. So that thickness is 0.01 centimeters. Remember, we want everything in centimeters. Our equation for energy loss is shown here, which is again the stopping power times the thickness in centimeters times the density in grams per centimeters cubed. So all our units are equal. We get the energy loss equation here. We just plug in our terms where our stopping power, when we look up from the E-star program, is 1.1 MeV centimeters squared per gram. The density of uranium, again, is around 18.95 grams per centimeter cubed. We get an energy loss of 0.2 MeV, so we have about 0.8 MeV of energy remaining in the electron after it passes through a 0.01 centimeter thick piece of uranium metal. We can perform the same calculation for graphite. Imagine that we have the same size, thickness of graphite, so 0.01 centimeters. Stopping power is listed here, 1.627 MeV centimeter per gram. The energy loss is shown to be 1/10 of what we get for the uranium, 0.0276 MeV. So the bulk of the electron energy remains with the electron. So the energy that is absorbed by the material is relatively low. This shows that obviously uranium would be better at stopping an electron than graphite. Higher Z, more electrons available for the fundamental interactions for slowing down the material. And here's the data that comes from the ESTAR program, stopping power versus energy. And we see some similar trends where we have larger values at low and high energies and a minimum close to 1 to 10 MeV. Unlike the previously described charged particle interactions, photon interactions with matter vary. They have some different properties. One of these being that photons can lose most of their energy in a few interactions or a single interaction. You also need more material for interactions than an electron, or for charged particle for that matter. And the average, similar to the other reactions, however, the average energy loss per ion pair formation is about 35 electron volts in air. Photon interactions with matter can be divided into three areas. One is the photoelectric effect. We have a pictorial examination of the photoelectric effect here, where a photon ejects electrons that are bound. Photon has a given energy, and this ejected electron has an energy that's equal to its binding energy, the photon energy minus its binding energy. So we utilize this equation right here, where this is the photon energy, the binding energy, the rest of the energy is imparted to the electron. Most of these photoelectric electrons come from the K shell, and the degree of the photoelectric effect is proportional to the Z, shown here, Z to the 5th of the absorber. So as an example, for 5% photoelectric effect, the gamma energy needed for different Z's is shown here. So for a higher photoelectric effect, one would use a lower Z. Two other effects are listed here, the Compton effect and the pair production. The Compton effect is a partial interaction, so the photon loses part of its energy to the electron. So imagine here we have an incident photon, we get an electron, and then the photon is scattered. So unlike the photoelectric effect, it's only a partial transfer of energy from the photon to the electron. The photon is scattered. There's a relationship between the energy for the photon and the electron rest energy. So we can talk about the electron rest energy, the photon energy, and that'll give us some minimum for the scattered photon energy. And it's also possible to observe a backscattering peak from this Compton effect. Compton effects are often seen in gamma detectors, where you see a large, where you'll see counts above the background that are energies below a main photopeak. A final method for photon interaction with matter is pair production. In this case, a photon converts its energy to the production of a positron and an electron. This is proportional to energy and Z. It's more common at high energy. In fact, there's a threshold. And this is often observed with a 511 keV peak, because if we produce a positron, it'll interact with another electron and form this annihilation peak. So that pair production, we see from here, we have an incident photon where a positron and an electron are produced. Now here's an evaluation of interactions of photons with different matter, aluminum, copper, lead. We have cross sections versus energy. And some of the trends that we see here, these are all from 0.1 to 10 MeV. We see that for aluminum, Compton effect is fairly dominant. For copper, the photoelectric effect is higher at the lower energies. And then for lead, the photoelectric effect dominates at the lower photon energies. Compton effect is dominant in the middle energies, and pair production is important at high energies. The other thing I'd like to have you take notice of this figure are the cross-section data. It's plotted against cross-section in aluminum. The cross-sections go up to 6. For copper, they go up to 14. And for lead, they go up to 140. So this indicates that the interactions with lead are by far the greatest. This concludes part 1 of the lecture on radiation reactions. In this lecture, we really focused on the interaction of radiation with neutrons, positive ions, electrons, and photons. In part 2, we're going to discuss dosimetry, radiation protection, and then end this lecture discussing hot atom chemistry. When you've completed this lecture, please move on to part 2.